There's an infinite number of parallel universes. There is an infinite possibility that there's a parallel universe.
In a time when science fiction starts to feel real, a young genius, often called the smartest kid in the world, has made a claim that could change how we see everything. At CERN, one of the most advanced research centers on Earth, scientists work to study the deepest questions about the universe. Now, a shocking idea has entered the conversation. A portal to another dimension may have been opened, and the person bringing this idea forward is the world's smartest kid, someone who many compare to a modern-day Einstein.
There is an infinite number of parallel realities with an infinite number of parallel dimensions that actually can create a powerful or less powerful form of God.
But how much of this can be taken seriously? Is this a real scientific breakthrough, or is it just a bold claim? Now, if there's any truth to it, the impact could be massive. It could change how we understand reality itself. So let's take a closer look at what's being said and how this young mind has connected his ideas to the possibility that CERN may have opened a doorway to another dimension.
Extract electromagnetic energy from everything around us and convert it into electrical energy. If there are other universes that are next to ours, and this actually relates to my theory of the Mandela effect and how the particle accelerator altered the weight of one.
Over the years, science has seen many gifted young thinkers. Still, very few have gained attention like Laughlin. Known by many as one of the smartest kids alive, he has shared theories that spark concern and curiosity among scientists worldwide. Much of this attention comes from his ideas about the Large Hadron Collider. At first, Max impressed people with his way of explaining how the universe works and how humans fit into it. But his more recent statements go much further. They raise some serious questions. Through detailed videos, he explains his thoughts in a way that draws people in, even those with a strong science background. Now, beyond theory, he has also shown interest in invention. And at just 13 years old, he introduced the idea of a free energy device. He claimed it could change how people live across the world. Now, if it's true, it could reshape everyday life in a big way. Now, since then, Max has become known for sharing ideas about the universe and the possibility of parallel worlds. He often talks about experiments at CERN and what they might mean for reality itself. Now, these experiments rely on the Large Hadron Collider, a massive machine built to smash tiny particles together and study what happens. The goal is to recreate conditions similar to the Big Bang. Now, Max believes that while these tests are impressive, they may have also caused unintended effects, possibly shifting our universe into another one. One of the key ideas in his thinking is that our universe is not the only one. He suggests it's just one of many, part of a much larger multiverse. According to him, there could be endless versions of reality existing side by side. He argues that humans were once on a single timeline, but something changed. During one of these experiments, an unusual event may have taken place. That event could have triggered ongoing shifts, moving us from one version of reality to another without us even realizing it. Today, the idea of multiple universes is something more people are starting to talk about. It challenges what we think we know. In Max's view, reality itself may not be fixed. He suggests that scientists at CERN may have detected unusual activity in space and time, and then tried to study or even influence it. This connects to the idea that portals between universes might be possible. Now, Max links this idea to the Mandela effect, suggesting that changes in reality could explain why groups of people remember things differently. To better understand these ideas, it helps to look at the Large Hadron Collider itself. This machine sits underground in a 17-mile-long tunnel along the border of France and Switzerland. It's the most powerful particle accelerator in the world. Inside the tunnel, beams of particles are sent crashing into each other at high speeds. Scientists then study the results to learn more about matter and the laws of physics. From Max's point of view, this machine may have done more than just collect data. He believes it could have caused a shift in our reality, moving us into a nearby universe. Well, concerns about the machine are not new. Even before it began operating, some scientists and observers were worried about what could happen. There were fears that the collider might create a black hole that could threaten Earth. One of the most well-known warnings came from Francesco Calogero, a nuclear physicist from the University of Rome. In 2000, he wrote an essay titled The Michael-Rias Experiment, a threat to planet Earth. His argument started a long debate about whether the collider was dangerous or simply a powerful research tool. The discussion reached a wider audience years later. In 2009, John Oliver covered the topic on The Daily Show. During the segment, a science teacher claimed that there was a 50% chance that the experiment could create a destructive black hole. Now, this worried many viewers. However, scientists working at CERN responded by explaining the facts. They showed that these fears were not supported by any real evidence. According to them, the collider is designed for research and discovery, not destruction. In the middle of all this scientific discussion, the idea of the Mandela effect comes into focus. Max Laughlin, known for his bold ideas, supports the idea that this phenomenon is real. The Mandela effect happens when large groups of people remember something that never actually occurred. This idea connects with Max's views because it questions how we understand memory and what we call reality. The term itself was introduced in 2009 by Fiona Broom, who also created a website to document her experiences. Her interest began at a conference where she spoke with others about her clear memory of Nelson Mandela dying in prison during the 1980s. In reality, Mandela passed away much later, actually in 2013. Well, as Fiona Broom continued these conversations, she realized something surprising. Many others shared the same memory. People recalled detailed news reports and even a speech from Mandela's widow, even though none of that actually happened. Well, this shared false memory became known as the Mandela effect. It also seemed to support Max Laughlin's idea that reality might not be as fixed as we think, but instead could be part of an alternate version of the universe. The Mandela example is just one case. There are others too. Some people remember Mickey Mouse wearing suspenders, while others don't. Another common example is the famous line from Snow White and the Seven Dwarfs, which many recall as "Mirror, mirror on the wall," even though the original line is different. These examples show how shared memory can drift away from actual facts, adding weight to the idea that reality might not be as stable as it seems. And while the Mandela effect raises questions about memory, scientists at CERN are focused on understanding the structure of the universe itself. Their main tool is the Large Hadron Collider, which allows them to test ideas in particle physics, especially those connected to the Standard Model. This model explains much of what we know about tiny particles. Even with the success of the collider, including major runs from 2010 to 2013, and again from 2015 to 2018, many questions remain unanswered. One of the biggest is dark matter. It makes up most of the matter in the universe, yet we can't see it directly. Scientists only know it exists because of the gravitational effects it has on galaxies and clusters. It acts like an invisible structure holding everything together, but its true nature is still unknown. The Large Hadron Collider was built in part to help solve this mystery and possibly change how we understand the universe. When the collider first started operating in 2010, there was huge excitement among scientists worldwide. Many believed that this machine would reveal answers to some of the biggest questions in physics. They were hoping for more than just the discovery of the Higgs boson, which was already a major achievement. They expected it might also explain dark matter. However, aside from confirming the Higgs boson, the early runs didn't deliver the other major discoveries. This left researchers still waiting, still searching for answers that seemed just out of reach. Well, after its second run ended in 2018, the collider was shut down for upgrades and maintenance. For 3 years, it remained offline, while engineers worked on improving its systems. Well, it finally restarted on April 22, 2022, marking an important moment in physics research. The third run officially began on July 5th, shortly after the 10-year anniversary of the Higgs boson discovery, which added a bit of extra importance to the timing. Whenever you hear about a newly discovered and unusual subatomic particle, there's a strong chance that it came from CERN. One example came in January of 2022, when scientists reported the discovery of mysterious X-particles. These particles were found within the quark-gluon plasma created by the collider, hidden among trillions of other particles. Now, they're called X-particles because their structure is still not fully understood. Scientists believe they formed very early in the universe, just fractions of a second after the Big Bang. At that time, the universe was extremely hot, filled with a dense mix of quarks and gluons in their simplest form. Before these particles could come together and form the protons and neutrons that we know today, a very brief moment took place. Well, during that time, a small number of quarks and gluons joined together and created short-lived X-particles. Scientists still don't fully understand how these X-particles formed, but if they figure it out, it could reveal what kinds of particles existed in the universe right after it began, helping us better to understand its earliest stages. At CERN, researchers tried to recreate these X-particles. They did this by smashing positively charged lead atoms into each other at extremely high speeds. Well, these collisions caused the atoms to break apart and briefly recreate conditions similar to the hot plasma that filled the early universe. A huge number of particles were produced, including the rare X-particles. But finding them was very difficult. Scientists had to go through around 13 billion collisions to spot them, which made the task extremely challenging. Well, the story of the Large Hadron Collider continues. In April 2022, it started operating again with even higher energy, reaching 6.8 tera-electron volts. Well, this marked the beginning of its third run, which is planned to continue until 2026. Scientists were excited, hoping that this phase would lead to new discoveries. But during this third run, something unexpected happened. On July 7th, researchers noticed a strange event involving Earth's magnetic field. A gap appeared in it and stayed open for about 14 hours. This allowed strong solar winds to pass through, which led to large geomagnetic storms and bright auroras in the sky. Well, the colorful lights caught people's attention, and some fans of Stranger Things even joked that it kind of looked like a portal for the character Vecna. Of course, that was just their imagination. So what caused this opening in Earth's magnetic field? It was actually linked to a rare solar event called a co-rotating interaction region, or CIR. Now, these are large plasma structures that form in space around the Sun, and they happen when fast-moving and slow-moving streams of solar wind collide. Like coronal mass ejections, these events can send shock waves and compressed magnetic fields toward Earth, creating strong space weather and visible auroras. The CIR responsible for this event reached Earth early on July 7th and triggered a G1-level geomagnetic storm, according to the National Oceanic and Atmospheric Administration. Now, this raises an important question. Should we worry about these magnetic gaps? Well, experts say that they're actually a normal part of how our Earth's magnetic field works. The field acts like a shield that protects us from solar activity. Now, these gaps can open and close from time to time, and they usually don't last long. In this case, it stayed open a little longer than usual, which showed that the field is not perfect. Harold Frey once compared it to a house with a window left open during a storm. The structure blocks most of the storm, but some effects still get in. In the same way, Earth's magnetic field absorbs most solar energy, but a small amount can pass through. This can sometimes affect satellites, radio signals, or power systems, though no major disruptions were reported in this case. At the same time, the third run of the Large Hadron Collider is an important step in a larger scientific effort. Well, during its first run, scientists discovered the Higgs boson, which helped explain how particles get mass. In the second run, they studied how this particle behaves and breaks down into other particles. These results strengthened our understanding of how mass works, especially for heavier particles. Now, in the third run, scientists expect to collect much more data, possibly doubling what they already have by the time it ends in late 2026. Well, after that, there'll likely be a long preparation period until around 2029 for further upgrades. When the collider returns in its next phase, it's expected to reach collision rates about 10 times higher than today. Looking even further ahead, the fourth run is planned to continue until around 2042, which could produce a dataset nearly 10 times larger than what Run 3 will deliver. At the core of physics at the Large Hadron Collider, or LHC, is the massive amount of data created when protons collide at extremely high energies. Well, protons are used because they're easier to control and accelerate compared to other particles. Even though they're not fundamental particles, protons are made up of smaller components called quarks, which are held together by gluons, the carriers of the strong nuclear force. Now, to understand what happens during these collisions, it helps to imagine protons like small bags filled with different particles, including quarks, gluons, antiquarks, and even heavier ones like the W and Z bosons that handle weak interactions and radioactive decay. When two protons smash into each other, the most common result is similar to two of these bags bursting open, scattering their contents and forming familiar particles such as protons and pions. But in some cases, only a few of those inner particles, like quarks or gluons, collide directly. Now, in those moments, their energy gets squeezed into a very tiny space before spreading out again into new particles, sometimes even heavier ones. These detailed interactions are what scientists study to better understand the basic structure of matter and how the universe works. In the early stages, the main goal of the LHC is to search for new fundamental particles that could point to unknown forces in nature. Some of these possible particles are expected to be very heavy and would decay into groups of quarks and leptons, releasing large amounts of energy. However, researchers do not expect clear discoveries of this kind during the current third run. Instead, they might find small statistical patterns or unusual event images that hint at something new. Now, these hints can guide future theories and experiments. Stronger confirmation is more likely in later phases, especially during the high-luminosity upgrade planned for the fourth run. Well, right now, there's a good chance to search for weakly interacting particles, including those linked to dark matter. These particles are produced through weak and electromagnetic forces rather than strong interactions, which makes them harder to detect. Because of that, collecting more data becomes very important. Now, dark matter particles do not leave direct signals in detectors. Instead, scientists look for visible particles that appear to recoil, which follows Newton's third law. By studying these recoiling particles, researchers can infer the presence of something invisible. Improvements to the trigger systems in the third run are expected to help capture these subtle events. With more data being recorded, the chances of spotting rare interactions become higher. While at the same time, CERN has introduced early plans for a future circular collider that would be even more powerful than the current machine. However, this idea has sparked debate. Sabine Hassenfelder, who works at the Frankfurt Institute for Advanced Studies, has raised concerns about the cost. She argues that there's no solid reason to expect new physics at the energy levels this future collider would reach. She suggests that the same resources could be used for other scientific projects, such as building a radio telescope on the far side of the moon or placing a gravitational wave detector in space. Now, these alternatives, in her view, might offer more reliable scientific results. Meanwhile, the LHC is still progressing through its third run, with plans for a fourth run ahead. Both are expected to add valuable knowledge to particle physics, leaving the question open about whether a new collider is even worth the investment. As the Large Hadron Collider continues its run, researchers are also focusing on improving how they analyze the massive amount of data being produced. Well, each second, millions of collisions take place, and only a small fraction can be recorded and studied in detail. To deal with this, scientists rely on advanced filtering systems that quickly decide which events might be important. These systems are constantly being refined to catch rare signals that could otherwise be missed. Another major focus is precision. Instead of only looking for entirely new particles, scientists are also measuring known particles with greater accuracy. Even very small differences from expected values can point to new physics. For example, if a particle behaves slightly differently than predicted, it could suggest the presence of unknown forces or hidden particles influencing the result. Well, this approach requires careful calibration of detectors and repeated verification of results. Collaboration also plays a big role in this process. Thousands of scientists from different countries work together, sharing data and comparing findings. This helps reduce errors and builds confidence in any potential discovery. Large experiments like ATLAS and CMS operate independently, but they often check each other's results. Now, if both experiments observe the same unusual pattern, it becomes much more convincing. At the same time, theorists are working alongside experimental scientists. They develop models that predict what new physics might look like in the data. These predictions guide researchers on what to search for and how to interpret unusual results. It's a constant back-and-forth process where theory and experiment push each other forward. Well, that brings us to the end of today's video. If you found this interesting, make sure you like the video and drop your thoughts in the comments section. What do you think the Large Hadron Collider might discover next? Don't forget to subscribe and turn on notifications so you don't miss the next video. Thanks for watching, and I'll see you in the next one.